All right, so section 3.2, modified discussion on differentiability. When does a function not have a derivative at a specific point? So the definition of this says a function will not have a derivative at a point, let's call it P, so a and f of a, your x and your y, where the slopes of the secant line so the slopes of the secant line, aka, remember, it's f of x minus f of a, all of that over x minus a, fail to approach a limit as x approaches a. So basically, the idea is that a function will not have a derivative if the secant line between f of x and that point does not approach that point. Okay? So, three ways that a derivative fails. You either have a corner or a cusp. An example of a corner is an absolute value function, because you have a very sharp corner. And remember, what does derivative mean? Derivative means the slopes at every single point. And what happens here is that the slopes here are positive, and then all of a sudden it jumps and it becomes negative. So the function, the derivative of this function, looks like a discontinuity. It kind of starts, it starts at positive 1, and then it jumps, and the rest is negative 1. So that's why the derivative does not exist at 0, so the derivative does not exist at that corner. Now a cusp is basically just like an extreme corner. So it looks like this. An example is f of x equals x to the 2/3, which, if you guys recall, is basically the same thing as me saying the cube root of x squared. And this graph looks like an absolute value, except it kind of does like one of those. So this is a cusp. It's like a corner. There's still, you have a very sharp corner where the slope suddenly changes at x equals 0. So there's an extreme corner at x equals 0. Okay? All right. Next one is the vertical tangent. A vertical tangent, an example of a vertical tangent is f of x is equal to x and 1/3, which is the same thing as saying the cube root of x. And this graph looks like this. So the graph starts off somewhere down here, and then at some point the slope becomes undefined, and then it picks up again. So at this point right here, the slopes of this function are undefined, which means the derivative does not exist in that area. Okay, so the slopes of secant approaches negative infinity or positive infinity from both sides. So it becomes almost undefined. So the slopes, as I get closer to this point, what happens? It's basically getting very, very close to being undefined, correct? So very, very close to either negative infinity or positive infinity. Same thing from this side. So therefore, the derivative at x equals 0 does not exist, D and E. And then the last one, which is the easy one to see, is the step function. When you have an actual discontinuity, so a step function. So an example is, let's just draw any step function. Starting here, it does one of those, and then from here, let's say it does like that. So what happens as the limit of x approaches 0 from the left? It's getting closer and closer to, let's say, -1. And then from the right, it's getting closer and closer to 1. So the limit as x approaches 0 of this function does not exist. And the whole idea is to be differentiable. The function must be smooth and continuous. Okay, so it must be smooth and continuous. So let's look at an example. So first off, we're going to graph this function. We have two functions here. You have y equals x, where x is less than 1, and then 1 over x, where x is greater than 1. So first I'm going to draw my x and y. And basically the point of discontinuity is going to be at 1. So at this point right here, my graph is going to change. So y equals x. Basically, if a graph starts at, if x is 0, y is 0. If x is 1, y is 1, but y at 1 is going to be an open circle because 1 is not included. If x is -1, y is -1, and so on, all the way down. So there is f of x is equal to x when x is less than 1. Now the next side, which is 1 over x. So when x is 1, this is 1. So what happens here is this actually closes back up. When x is 2, y is 1/2. When x is 3, it's 1/3. When x is 4, it's 1/4. So you can tell that this graph kind of does one of these. Now remember, I don't care when x is 0 because the limitation here, x has to be greater than or equal to 1. So there's the graph. Now the next question is f of x continuous at x equals 1? Check the 3 parts of the definition of continuity. So let's recall, what are the 3 parts? The 3 parts of discontinuity. 1, does the limit as x approaches c, whatever, so basically 1, from the left of f of x equal the limit as x approaches c from the right of f of x? So if we check that, does the limit as x approaches, so let's check number 1. The limit as x approaches 1 from the left of f of x is what? As I approach 1, my limit is 1. And does that equal the limit as x approaches 1 from the right? So as I approach 1, my y is 1. So far so good. 1 checks out. Part 2 says, is f of c is defined? F of c is defined. So to check number 2, f of 1 is what? F of 1 is 1. So, yep, it's defined. And then the last part says, does the limit as x approaches c of f of x equal f of c? Now, because these two are the same, that means the limit does exist. So part 3 does check out because the limit as x approaches 1 is 1, and f of 1 is 1. So because these two are the same, it checks out. So, yes, it's continuous because we check the 3 rules. Now the last question says, does f of x have a derivative at x equals 1? Use the definition, which requires looking at the left and right hand limits of the function. So, using the definition of derivatives, let's remember what that is. It's basically, oh, and we're going to do it both for the left and for the right hand because it is a two-part function. So, remember the definition of derivatives is the limit as h approaches 0 of f of x plus h minus f of x, all of that over h. The only difference here is we're going to do it as h approaches 0 from the left. So I'm going to have a minus here, and as h approaches 0 from the right. So let's do them. So the limit as h approaches 0, I'm starting from the right. So because it's from the right, that means that which function are we going to use? Okay, so because it's from the right, that means it's going to be in the positive direction. So I'm going to basically be using f of x equals 1 over x, okay, from my example. So we're going to be using this one because we're approaching it from the right, the positive side. So I'm going to plug this in. So 1 over x plus h minus 1 over 1. Okay, because remember my x is 1. All of that over h equals, basically find the common denominator, right? So this guy needs an x plus h, so whatever we do to the bottom, we do to the top. So we're left with 1 minus 1 x plus h, 1 times x plus h, all of that over x plus h, all of that over h. And now, and I don't know why I kept this as an x, I apologize. This should be a 1 because the derivative is at 1, so this should also be a 1, a 1, a 1, a 1, okay? So now we're gonna simplify and then flip the guy and multiply. So let's simplify first. 1 minus 1, what are we left with? We're left with negative h over 1 plus h, all of that over h. Now flip the guy and multiply, so this is h over 1, so I'm going to multiply by 1 over h, and that's gone. So we're left with negative h over h times 1 plus h. So what happens to the h's? They're gone, so we have negative 1 over 1 plus h. And now when we plug in 0, what do we end up with? The answer is negative 1. So we have to do this again now for h is approaching 0 from the right. when x is 1. So now we're going to actually use the other function, which is f of x equals x. And this one's a little bit easier. So x is 1, so we're going to plug in 1 plus h minus 1. Remember, we're plugging it into that function x. All of that over h. So 1 minus 1, that is gone. And we're left with h over h. And then that simplifies down to positive 1. So because the limit as h approaches 0 from the right is negative 1, and the limit is positive 1 as it approaches it from the left, so no, the derivative at x equals 1, so no derivative at x equals 1 because the left and right limits are not equal. Okay, so you can see a lot of the same is still the same, okay? And based on our definition, I think you realized in that graph that basically you do have a corner. It's like a corner slash cusp at that point. So you should have known just from the picture that that derivative does not exist at 1. Okay. All right, differentiability implies continuity. So what this means, so what the theorem says, is exactly what we just did. If f has a derivative at x equals a, whatever that point is, then f is continuous at x equals a. Okay? So basically what we're saying is since a function must be continuous to have a derivative, then it has to have a derivative, aka slope of the tangent, to be continuous. Okay? So the example that we're going to do here, on your page it looks a little different, so let's go to the next page. The example that I'm going to focus on, I'm going to use the interval notation, and at what point of the domain does the function appear to be differentiable, continuous. So we're going to consider the function f of x is equal to x 1/3 plus 2. That's going to be our example. So I'm going to graph this, okay? And if I graph it, I'm going to use my graphing calculator, and then this is kind of what I get. So when I graph this, I end up with a graph when x is 8, y is 0. So 8, the cube root of 8 is 2 plus 2. That should have been 4, unless let me just double check my function. I must have graphed minus 2. But when x is 8, so the cube root of 8 is 2, plus 2, it's actually going to be 4. I think this is supposed to be a minus 2. Now that I think about it, maybe not. I don't know what I just did. And I do not have my calculator with me. Okay. I can't pause this video because if I pause it, it's gonna discontinue. So hold on one second. Let me get my calculator. Okay, I did graph the wrong function. And let's get rid of that table. So to get a few points, oh, that's why. At -8, I was plugging in 8, so no, I was correct. At -8 is 0. Brain fart, sorry. At -1, it's 1. At 0, we got 2. At 1, it's 3. And then at 8, it's 4, which makes sense. 3, 4, 5, 6, 7, 8. It's 4. All right, so there's the graph. So the question is where is the graph differentiable? It doesn't look at, but if you look at the table of values around 0, okay, you basically can see how it jumps from 2 to 3. So at 0, if you think about it, at 0.0001, it's about 2.001. And then it's getting steeper and steeper, even though my graph does not show this, okay? But it is getting steeper and steeper. So based on this, where is it differentiable? Because this is technically a vertical tangent, even though it may not look like one because of how I'm graphing it, but I will actually show you guys how you can zoom in, and then you can see on the calculator the linear, I wish I can zoom in on my calculator. You guys can probably fast forward a lot of my mumbo jumbo right now, but you can zoom in and you can kind of see that there is a vertical tangent right there, okay? I don't want to waste too much time using the calculator, but let's zoom in a little bit. See that? Okay, so the more you zoom in that area, you can see that there is a vertical tangent. So at some point, the slope becomes very, very, very close to negative infinity or positive infinity, depending on which direction you're coming from. So where is the graph differentiable? Where does it have a slope? It has a slope everywhere except at x equals 0, except at that vertical tangent. So where is it differentiable using interval notation? We can say from negative infinity to 0, 0 is not included, and then from 0 to infinity. Where is the graph continuous but not differentiable? So it is still continuous based on the definition of continuity. It still approaches 0 from the left and right at 2. So the limits there, f of 0 is 2, so it is continuous, but not differentiable at x equals 0. And then C, where is it neither continuous nor differentiable? None. I mean, okay, it's not differentiable here, but it is continuous here. Okay? I'm going to show you guys just one more example just to kind of make sure that you understand what I was just saying. So here's another graph. I'm going to focus kind of on a ugly piecewise function. Okay? So here is my graph. And let's say it picks up over here. 1, 2, 3. And it drops over here. But we have the whole, let's say right there. I'm just making a random graph right now. Okay, there it is. So to answer the 3 questions, where is the graph differentiable using interval notation? It's basically differentiable. You have a slope starting at -2. You do have a slope here because if you pick 2 points, the slope of the secant, if you pick 2 points, you do have a slope. So it starts at -2. You have a slope continuously all the way to -1, let's call that. But at -1, we do not have a slope because we have a corner. Okay, there's a corner here. And then it picks up at -1, not included. You do have a slope all the way to 0, but 0, I don't know why I just put a negative over there. 0 is obviously not included because it's a hole, not because of any other reason. It picks up at 0, but at 0 we are not differentiable because there's a jump. So it picks up at 0, but 0 again is not included because of that jump. Okay? So it picks up at 0 all the way to 2 because there's a hole here. So we obviously do not have a slope at that point. So 2 is not included. And then it picks up again at 2 all the way to 3. And then 3 is included because that's a point. Okay? So part B says, where is the graph continuous but not differentiable? So we said it wasn't differentiable here, but it is continuous here. So at x equals -1, now it's not continuous here and not differentiable. It's not continuous here and not differentiable, and that's it. So this is the only place where the graph is actually continuous but not differentiable. And then the last part says, where is the graph neither continuous nor differentiable? So it's not differentiable, remember, not continuous at this jump, so at x equals 0, and it's not differentiable at a removable discontinuity at x equals 2. And we agreed before that it's also not continuous, not differentiable. All right, the last example is kind of what I just showed you guys with the last definition, local linearity. It's just zooming in to see the differentiability. And it's kind of what I just showed you guys with this example right here. The only way I can actually see it is by zooming in a lot, and then I was able to see the vertical tangent. But by graphing it, just by using -1, 0, and 1, I was not able to see that this was not differentiable. It looked like an actual slope. Okay, enjoy the video. You'll probably be able to fast forward through a nice amount of this because of my stalling, but good luck and enjoy.